So welcome back, and we have seen what is the Carter's gap coefficient, that is KCS. So we were discussing about the reluctance of the air gap with slotted armature. Already we have seen from equation 4.15 that what is the reluctance of the air gap with smooth armature. Okay, that is when the surfaces are smooth. What is the reluctance? What is the reluctance then? According to 4.15, that is Lg by mu naught YSL. That was the reluctance of the air gap without any slot. But when we consider the slotted armature, this is the case. That is Lg Sg is equal to Lg by mu naught Ys dash L. So what is Ys dash? Ys dash is nothing but Ys minus Carter's gap coefficient multiplied by Ws. Okay, now we take a ratio, that is ratio of reluctance of air gap of slotted armature to reluctance of air gap of smooth armature. Okay, that is nothing but a new term, that is KGS. We find the ratio of reluctance of air gap of slotted armature to reluctance of air gap of smooth armature. So you have the two equations, that is 4.21 divided by 4.15, equation 4.21 divided by equation 4.15. When you do that, you will get the value KGS as Ys by Ys minus KCS Ws. Okay, so that is, this KGS is called the gap contraction factor for slots. Gap contraction factor for slots. So how do you get KGS? You take the ratio of two equations, that is 4.21, equation 4.21 divided by equation 4.15. I'll give the, you have the materials, I'll provide it and you can see it from the material. Okay, both these equations, you find the ratio, you'll get KGS as this one. Okay, that is according to 4.22. Now, I told that there are radial ventilating ducts. Okay, so this is the overall length of the machine. This is my armature, this is my shaft. Okay, and this is my stator, from where we have the generation of flux as well as MMF. Ampere turns are here. So MMF in the air gap will have flux, and these are the slots and these are the teeth. Okay, and in between you have the ducts, and the ducts are, each duct is having a width of WD, and there may be ND number of such radial ducts. So what happens? Initially this was my length, of the machine, overall the main dimension of the machine. But since due to the presence of the radial ducts, what happens? This is a hole actually. So what happens? The length reduces by a small margin. Okay, so what is, how much it reduces? Here also you can proceed the same way. You can get this relation, that is the effective axial length is L dash, which is nothing but the total length L minus KCD, the Carter's gap coefficient for ducts. Earlier we have seen the Carter's gap coefficient for slot, that was KCS. Now Carter's gap coefficient for ducts, that is KCD multiplied by not WD alone but ND into WD, because WD is only for a single duct but it has ND number of ducts. So ND into WD will be the total width of radial ducts multiplied by KCD. So by this much margin, the effective length reduces. So the L dash is nothing but L minus KCD ND WD. Okay, now in the similar way, just like what we have found for KGS, what was KGS? Reluctance of air gap with slots divided by reluctance of air gap without slots. Now we are taking another ratio, similar ratio, that is a ratio of reluctance of air gap with ducts to reluctance of air gap without ducts. So again you can see that reluctance of air gap with ducts is nothing but what, that is Lg by mu naught Ys dash and L dash. What is L dash? L dash is nothing but L minus KCD ND WD. What is the reluctance of air gap with ducts? That is Lg by mu naught Ys dash multiplied by L dash. Okay, where L dash is this value, divided by what is the reluctance of the air gap without ducts? That is Lg by mu naught Ys dash L. Okay, Ys dash L. So all other terms gets cancelled. What is remaining is L by L minus KCD D, ND, WD. So this is the gap contraction factor for ducts. Okay, so we have seen what is KGS and what is KGD. Now considering the that is overall thing, we are bringing everything together. What is the reluctance of air gap of smooth armature without ducts? That is Lg by mu naught L into Ys straight. Okay, smooth armature without any ducts, Lg by mu naught L into Ys. What is the case or reluctance of air gap with slotted armature with ducts? That is Lg by mu naught L changes to L dash and Ys changes to Ys dash. We know what is the value for L dash as well as Y dash. If we find the ratio of the reluctance of slotted armature with ducts, that is this equation divided by this equation, what we get is Y by Ys dash into L by L dash. We know what is Ys. Ys dash is already we have seen, that is Ys minus KCS Ws into L by L minus KCD ND WD, and this is nothing but KGS and this is nothing but KGD. So what is a new term KG? KG is nothing but the product of KGS and KGD. And what is KG then? KG is nothing but what the ratio of air gap of slotted armature with ducts to reluctance of air gap of smooth armature without ducts, and it is called total gap contraction factor. We had gap contraction for slots as well as gap contraction factor for ducts. So what is KG? Combining everything, we'll get the total gap contraction factor, which is KG, which is a product of KGS and KGD. Okay, now and the value of kg is more than 1. Okay, you can easily find that also. The value of kg is more than y. Kgs is more than 1. Kg, what is kg? Kgs, ys is numerator is greater than denominator, ys by ys minus. So this term is greater than 1. Again, you can see that this term is greater than the denominator, that is L is greater than L minus this term. Okay, so again this value is also greater than 1. So overall kg is also greater than 1. Now for induction machines, you can see that stator as well as rotor are slotted. So for finding KGS, we have to find the gap contraction factor for stator slots as well as rotor slots. So gap contraction factor for stator slots is KGSS and the gap contraction factor for the rotor slots is KGSR. You find the product of these two, you get KGS. Okay. Now KGD is common because that is confined to ducts. Okay. Now I told that the gap opening, the slot opening is not uniform throughout. Okay, for semi-enclosed slots, opening width is different from that of the bottom slots. Okay, this width is not the same as here. So we take, instead of WT for semi-enclosed slots, we take WO instead of WS. So the Carter's gap coefficient, gap contraction factor for slots, KGS changes to Ws by Ws, the Ys by Ys minus KCS WO. Instead of Ws, we have WO. Now we are going to the main last equation, that is we are finding the MMF in the air gap. Okay, so we have an equation, we know an equation, well-known equation, that B is equal to mu H, where B is the flux density and mu is the permeability and H is the magnetizing force, that is ampere turns per meter. Okay, and as we are considering the air gap, mu is equal to mu naught, so we can write it as B is equal to mu naught H. From here we get the value for H, or AT by L, that is MMF per meter is equal to B by mu naught. So mu naught, we have the value 4 pi into 10 raised to minus 7. If you substitute the value of pi and multiply everything, we get that the MMF per meter for air gap is 8 lakh B. MMF per meter for air gap equal to 8 lakh B. How do you get that? That is H, that is 80 per meter is equal to B by mu naught. Mu naught, if you substitute the value for pi, what is for that? 4 pi, 4 into 3.14 into 10 raised to minus 7. If you substitute that, you get a value close to 8 lakh. So 8 lakh B. Okay. Now, how do you calculate? H is nothing but 80 per meter. So how do you get the MMF for the overall length? ATG is equal to MMF per meter into length. That is 8 lakh into B into the air gap length LG. But we have seen that an air gap is not uniform. So we have made some assumptions and we have made some calculations. And with respect to that, we have a factor called kg. So ATG, that is air gap MMF required ATG is equal to 8 lakh kg BG LG. Now is two small substitutions so that we can conclude these two things, that is B we can write it as flux per pole divided by AG, that is area per pole, actual area of air gap per pole. Actual AG is very important, actual area of air gap per pole. I'll show pictorially this one, AG, actual area of air gap per pole. So I can bring this kg down here, so that means 8 lakh 5 by AG by kg. So AG by kg I can write it as AG dash, that is the actual effective gap area, that is the actual effective gap area. You see that this kg value is greater than 1, so f value divided by a factor greater than 1, so what happens, AG dash is less than AG, so that means the gap contracts by a factor kg. Okay, now this same equation I can write in another form also, that is here, that is I can combine kg and lg. So what happens, 8 lakh B into kg and lg. So you can tell that this product is called the effective air gap length. So effective air gap length lg dash or lge. So sorry, lge is nothing but kg into lg. You can see that this effective gap length increases by a factor kg. Okay. Now we are moving into the last point. So I just explained what is AG. What is AG? AG is nothing but the actual area of air gap per pole. Actual area of air gap per pole. So this is the air gap. You have so many poles. I am considering only one pole and its corresponding area. So this is the flux distribution under this pole. So this is the actual area under this pole. Area of flux distribution under this pole. Okay, this is this space is this much space is actually nothing but the pole pitch. Okay, so if you want to find the AG, then the pole pitch multiplied by the length, overall length of the machine will give AG. That is, this much is the length of air gap covered by this pole, and that length multiplied by the overall length of the machine will give the area AG, area covered by one pole. Okay, so this is called a pole arc also, because when you see a pole, it looks like a cylinder, or you can see it as an arc. When you see the front view, it seems like an arc. So arc has a length, so that is called pole arc. And this is my LG, and this is called pole body or pole tube also. And this is this much region we have minimum reluctance. So maximum flux will become confined to this area. Of course, fringing of flux will be there towards the end, towards the edges, and here you can see the fringing, and you can see the distribution of flux density. That is, flux density will be maximum between the at the low reluctance point, and it will be reducing towards the this portion, that is this region. Towards this region the flux density will be reducing. Okay, so when you find the average, this is my B average, and my maximum flux density is BG. Okay, which is straight under the pole tube. Okay, now we have one more thing to discuss, that is a factor called field form factor. So what is field form factor? It's the ratio of B average by BG. Okay, so we'll just know what is B average, that is flux per pole by area per pole. Flux per pole we have already seen, that is phi. Area per pole we have already seen, that is the pole pitch. What is pole pitch? This is my pole pitch. This is my pole pitch. So this coming. This is my pole pitch. This pole pitch multiplied by the overall length of the machine, I'll get the overall area under a pole. So that is actually area per pole, that is pole pitch. That is, what is pole pitch? Pole pitch is nothing but the distance between the two centers of adjacent poles, that is pi d, the total perimeter divided by the total number of poles, will get the pole pitch, multiplied by length, I'll get the area per pole. So flux phi by pi d by p into L will get B average. So B average by BG, I'll get field form factor. There is also one more equation. These equations are very important in problem point of view, that is pole arc by pole pitch. It is also given as psi. So these are the equations which are very much needed for problem point of view. So you have to try the example 4.1, 4.2 and 4.3 as an